Hey everyone, my name is Ashley, and today we'll be going over question 2 from the CSM worksheet, Balanced Search Trees and Tries. So question 2 just contains a bunch of potpourri questions about 2-3 trees. So let's move on to the first one. So part A asked us, for a node in a 2-3 tree with n values, what are the possible numbers of children that each node can have? And what if the node is not a leaf? So let's answer the questions one by one. So the first question asks, what are the possible number of children that each node can have? So let's break this down into cases. So for first case, the node contains one value. So if it contains one value, it can either be a leaf node, where it means it has 0 children. I'm going to say children equals 0. And then we have, and if it has one value, that means to get to one value is the only way to get to one value is if you had like 2 nodes, or like pretend there's like a number here, like 1 and then 3, and then you add a third node. The thing is, 2-3 trees cannot have 3 values in a node, so you break it up, and then it becomes this. So 2 goes up here, and then 1 goes here, and 3 goes here, because the middle value would always go up. So that means the only way to get to a single node is by splitting what would have been a 3 node, and then that would result in 2 children. So that's the first case. The second case is the node has 2 values in it, so it's n equal 2. So there's always an option for it to be a leaf node, like this was before we added the 2, and that means there's no children. And then the second option is that we have this value, and then we just we add 2 more values to it, so that we have another child 5, another value in this node 4. So what this means is that once we have this, this can have up to 3 children because there's 2 nodes in the value. So you can have 3 children. So those are the 2 possibilities, and there's n can only equals 1 or 2 because it's a 2-3 tree. So that's how the different possible numbers that I can have. So it can either have it for if n equals 1, it can either have exactly 0, 2. If n equals 2, it can have exactly 0, 3. And then let's move on to the case if the node is not a leaf. So what that means is that if it's not a leaf, it cannot have 0 children, because that's what the definition of a leaf. So if it doesn't have 0 children, we just take out the 0 in each option. So n equals 1 would have exactly 2 children, and n equals 2 would have exactly 3 children. So that's how you find out how many children it can have if it's not a leaf. So let's move on to part B. So instead of splitting an overstuffed node by moving the middle value upwards in the tree, suppose we want to move the rightmost third value of a node. Can we still guarantee the idea of a balanced binary search tree with 2-3 trees using the splitting method? So, so what this question is asking is that can we still have a balanced binary search tree if we have a splitting method where instead of like splitting the middle node, like as we were doing here, like if we had 1, 3, and we added 2, it would become 1, 2, 3. But instead, it would actually become 1, 2, and then 3 up here. And this would not guarantee a balanced search tree because what this is doing, what the original method is doing, is making it symmetric. So the reason we choose the middle value is that it's exactly between the 2 values. So you can look at this and you know everything to the left of it is less than or equal to, everything to the right of it is like less than or equal to as well. So that means you can exactly know what values are on each side. However, if you put the rightmost, everything's going to be like skewed to the left, and we don't have the same like amount of symmetry. So this will not be balanced. Okay, so let's move on to part C. What is the maximum height of a 2-3 tree with n values? So the maximum height of a 2-3 tree is if all the levels are full. So basically when a 2-3 tree reaches its maximum height, it looks like a normal non-binary search tree where all the nodes contain a single value. So just to give you a reminder, normal BST looks like this. Everything contains a single value. And this is what the maximum height of a 2-3 tree can have with minimum like n values. And as we discussed before, like in the past, we've learned that the height of a tree is equal to log 2 of n, um, being n being the number of values. So this is how you calculate it. And in the 2-3 tree case, we want to floor divide. So we want if it's a like fraction, we want to round down to the nearest number. Okay, and moving on to part D, it asks us, is it possible for the leaf nodes of a 2-3 tree to have different distances to the root? If not, they want to explain why, and otherwise, provide an example of a 2-3 tree that satisfies this condition. Okay, so before we start answering this question, let's review how like 2-3 trees gain height. We learned that 2-3 trees gain height by splitting. Like for example, we had like 1, 2. We had like one node here. We add a third node, and then it splits. And this is how it gains an extra layer. So and this is the only way it splits. You add at the bottom, and the node becomes too like stuffed, yeah, it moves up. And if the node above it's too stuffed, it keeps moving up until it creates a new level or finds a node that's not stuffed. So one important thing to note about this is that both sides increase at the same level, or like both sides increase at the same rate. So when you add a level, all sides are balanced. There's no one like node that's like one below everything, because that's just because it doesn't split until it's like absolutely full. So as a result, it's not possible for a BS or a 2-3 tree to fit this condition because it always splits symmetrically. So like due to the like symmetric split and is why you can never have like leaf nodes being having a bigger like different distance to the root because it's always going to be equal distance from all the leaves. But yeah, that's how you solve these 4 parts of the CSM worksheet like Potpourri question. Hopefully this helped you guys, and I'll see you guys next time. Bye.